Right, so like I said, welcome to CSE IE 598, Bio-Inspired AI and Optimization. I'm Ted Pavlic. I'm an associate professor here in Sky, also in the School of Life Sciences of a joint appointment. And so today I just want to go over the policies of the course, and then eventually get to kind of the technical motivations of what we'll be working on for the rest of the semester. So quickly, first things first. Let's deal with the syllabus stuff. So this is on the Canvas site, which has been published last night. So that should be available. But some highlights here. So like I said, this is 598, bio-inspired AI and optimization. We'll talk about kind of the motivations of what we're going to be going over here today in just a second. But first, just kind of go over the administrative stuff. So in-person class, but I'm going to make every ability to record the lectures. There's not going to be an attendance requirement per se, but there is not also going to be a formal textbook that we're using. There's going to be materials that will support each lecture that I draw from that are posted, but so the main kind of source of the material and the flow of the course will be through me. But all of the lectures, as long as there's not a recording error, will be archived. And so if you miss a class or whatever, then the lectures and a lot of the times I will be taking notes on the tablet and projecting, and all of the things that I write here will also be archived on Canvas. And you can see examples of that from previous semesters courses that are also linked from the current Canvas site if you want to see how this ran in those semesters. So that's kind of the expectations there. So prereqs, what am I kind of expecting from you? So there's no formal course prereqs for this, but I'm kind of expecting that there's some familiarity with a little bit of mathematics. And so there will be, because this is an optimization course, a little bit of a focus here and there on things that are calculus-y occasionally. So a lot of times we work with non-differentiable complex objectives that we're trying to optimize, but at least at first, being able to sort of recognize a derivative and those sorts of things is probably helpful. And the other thing is you will be doing some of your own programming work. And so, a few exercises and things like that. I don't have a restriction on what tool or language that you use to answer these responses, though. So if you're most comfortable with Python, that's great. If you want to do sort of scripting in MATLAB, most of these will also be, fine with that. There's not like a fancy UI that you'll have to build with these. Java, NetLogo, Excel, all, different, whatever sort of tool makes sense for that particular challenge is fine. So I'm not looking for those specifics. Also, the programming assignments that we're doing most of them will not be graded with formal unit tests. So there won't be an expectation that it has to be able to load in a particular environment and take certain sets of inputs and produce certain sets of outputs. And so there will be some flexibility there, because for most part, the assignments that you're going to be doing are going to help you explore some of these concepts and give you an opportunity to try different things and then demonstrate through, say, graphs, what you've learned by trying those things. So that's kind of what I'm expecting of you kind of coming into this. And um, otherwise, what else can you get from me? So here's my kind of contact info. Email is usually a great way to contact me, but I'm also fine if you want to Slack message me, if you want to DM, that's totally fine. If you want to send me a Canvas message, that's also it works well. I have I have two offices, one in the Brickyard, one in ISTP1. So I split my time between those. But office hours, especially because in places like the Brickyard, there's access issues even to get even if you have access to the elevator, sometimes you don't have access to all the floors. So I've been doing office hours over Zoom. Usually that works well. If that doesn't work for you, then we can make an appointment and figure out how to do it in person. So there's an instructional staff page on Canvas, which right now has got a Zoom link there, and I'll post once the schedule settles a little bit. So hopefully later this week, I'll post an office hour time for that time. But there's always an opportunity to ask for an appointment if that time doesn't work for you. There is a grader for this course. The grader is the responsibilities of the grader is not the same as a TA. So there will be assignments that you'll do that we'll talk about that the grader will help out in grading, and you can reach out to the grader if there's a question about one of the grades after it's returned to you, but the grader cannot provide general help. So if you need sort of general help, topic help, things kind of looking ahead to an assignment or just general questions, then come reach out to me. Because the grader's really only there to do that grading. Then again, we'll get into this in detail here, but, basically this semester, we're going to survey a range of different um, intelligent approaches to solving hard problems that were inspired through natural systems. Those natural systems will be primarily biological and physical, but there will be some references to psychology as well. And so after all of that gaining exposure and working in these assignments, then I'm hoping that you'll gain some familiarity to some of these tools, which these tools are tools that are already built into many, if you were to go out to work in industry and need to, do a numerical optimization. And some of these nature-inspired tools are already just built into the platforms that are working there. So it's good to have some familiarity to know what these things are, or to know that the API exists. If you're writing this yourself, then you can say, wow, I need to solve this complicated multi-objective high dimensional problem. I only really at this point, you've probably these types of problems, if you have any background with them, you might say, well, I've done this in reinforcement learning. I've done sort of an RL-like problem like this. And this is going to be alternatives to that. So what are some different approaches you can go that might take you a different way, that might be faster, that might be more presentable, and so on. So that's kind of the primary thing. So just being able to encode these challenges in a form where you can put them in to these types of tools. But then also, I want you to know how some of these tools work. So we will, how do you implement these? And so we'll implement very simple versions of them in this class, and then talk about the elaborations you'll find in industrial tools. And then kind of, along with all of these things, then I also just generally want you to gain familiarity with some of the natural background that inspired these tools. And so we live hopefully in, a more interdisciplinary world where it's sort of beneficial to kind of see how problems were identified and solved in other areas, and to what extent can those processes from those other disciplines sort of enrich or enhance the way you look at your problem set. So that's something that this is hopefully helping to support. Anyway, so let's get into sort of the nitty gritty here and see if there's any questions. So what is required? Like I've kind of mentioned before, there's no required textbook that I'm asking you to buy or anything like that. If you go onto the Canvas site, then you'll find that there's a bunch of these units that in each unit, there will be some learning outcomes for that unit, what I'm expecting you to get out of that particular unit. And then there's a whole group of readings. And now it's a long list for every unit. Those are the readings that I just sort of thought, it would be kind of cool if I grab a little bit from this paper and this paper and this paper. And so I've put them all in there as sort of an artificial kind of set of chapters for those units. I'm not expecting you to do all of those readings. There will be occasionally an assignment where it might say, hey, go look at this reading. How did they do this? Can you elaborate on that? That sort of thing. And that happens with one or two of the units. But for the most part, those are just there for your reference if you need additional reading. So they're not sort of meant to be kind of weekly readings. There just would be too much for it if it was. So there's no required reading materials. If you are looking for some text to sort of help you through some of these things, if you go to the course information module on Canvas, I have a list of 4 good texts that cover the topics that are covered on this course, and I have some links to where to find them. So those might be good support if you're finding that you need them, but they are totally auxiliary, optional, not required. So like I said, on Canvas, if you go into the Canvas page, if you click on modules, you'll see that the course material is split up. We mainly focus on trying to cover these 8 units here, starting with evolutionary algorithms, ending in artificial neural networks. But if time permits, we might get into CAs and then stochastic policies and distributed automation. But usually it's there's some flexibility in our timing, and so usually we don't quite get into these. We might get a little bit into CAs, but these are kind of the core units, these 8 here. And like I said, if you go into Canvas, go into modules, you click on this particular unit, then you'll find that's where the assignments related to that unit are, and any supporting readings for that unit. So what about these assignments and things? So the way the course is set up is that this is the weightings of things here. I try to make this not a lot of burden, but provide a little bit of incentive for you to do work to sort of to help you have a kind of a formative experiences along the way without feeling like you're working all the time. So one of the things that I just do every week is I call them these muddiest point reflections. These are things that I read. I'm not asking for very much from you. So you'll notice that on Canvas, at the end of each week, there's an assignment that's in your to-do list, which if you click on it, it's like a little Canvas quiz where it's got 3 little boxes, and it asks a sort of a simple question along the lines of, what were the main topics covered this week? What were the most difficult topics covered this week? And what more would you like to learn about? Each one of those, I'm not looking for much. So a sentence or two at most, a few words is fine. But it's a way that when I then view the aggregated version of all of these things, I can go through and get a quick spot check of, all right, how did everything how was everything received? And what were are there common points common difficulties among a bunch of students that I maybe can address is if we're still in the middle of that unit. And so then they're just generally, it's interesting for me to read, and I think it's also helpful. It's been shown just for you to reflect on that in that high frequency. At the end of this week, what did we talk about this week? Well, let me just think about that, and it usually helps retain that. So I'm not looking for very much here. Like that's like 3 sentences every week. And then the lowest 2 of those are dropped. So you just 2 of those you can just skip. And then the less frequently than that are these so-called unit concept checks. And so for each one of those units, and so there's really only 8 units because those other 2 are bonus if we get to them. So there probably won't be concept checks there. And I dropped the lowest 3 of these. And so you really only have to do 5 of these things. These are going to be 4 or 5 question kind of quizzes at the end of every unit that just are summative things to sort of say, these are the things I'm hoping you took away, and to just sort of assessing how well you got those things. And so occasionally those might reference one of those readings and force you to go out and read that and reflect on that based on what we talked about in class. But but most of the time they'll just be relatively simple. Here's a problem. What's the answer to this problem type of thing. The more and that's actually a significant chunk there. So these are pretty easy, but that's a significant chunk of the score. These unit mini projects, these are optional ways to do a little bit more in every unit. So again, there's only 8 really units that we focus on. The other 2, hopefully we get to. And in each one of them, there's one of these mini projects. The lowest 5 are dropped. So that what I'm communicating there with that is I'm only expecting you to do, like 3 of these things. So you can do more, but it helps reduce the grading burden on us, and it also helps reduce the burden on you if you take advantage of these lowest 5 that are dropped. I do require everyone, because it's foundational, to do mini project 1. So that first unit, everyone will do. But then after that, you can sort of, if you want to do them all, that's great. If you only want to do 2, that's totally fine. I'm not going to look, it's you're not going to give yourself a lot of margin in case one of them scores low, but that's kind of the idea here. So what these mini projects are is, look, we'll see there's this final project where you're going to do something a little more in depth. The mini project allows you to do kind of a miniature version of that where, if let's say we work with a multi-objective genetic algorithm, that unit. Well, so then in that mini project, then you might be given the task to explore using a multi-objective genetic algorithm on a particular set of complex test functions and summarize what you find along with that sort of exercise there. And you'll summarize it in kind of a report format that sort of mimics the short form extended abstract that you'll do at the end of the semester. So that's kind of what these mini projects are for. And then just to keep things conventional during finals week, I will do a take-home Canvas-based, not proctored final exam that will go over. It's sort of like it's kind of like these concept checks, but all at once. So that's what kind of that's for. And then the biggest part of this, which is why this can be used in your portfolios for the master students who have portfolios here, is this final project, which is 40% of the score here. And the final project here, for a number of reasons, I do as a group project, but given that it's a relatively small course this semester, I'm okay with groups of two. And so the idea here is that you get there'll be milestones throughout the semester. So somewhere mid-semester, so you don't have to worry about that for a few weeks. You basically submit your team names. And then and so on and so forth. What as it describes here later down here in the syllabus, what the final project is for is, so we will describe through the 8 major units a wide variety of nature-inspired intelligent algorithms for solving problems. But there are a bunch more that are similar to the ones we talk about in class, but we won't have a chance to talk about specifically. So I have prepared a list of a wide range of the ones of these others that we don't go over. And for this project, I basically want you to look through that list. And if there's another one that you find that's not on that list, that's possible to bring up as well and say, I would like to do my project on this, this chaotic catfish particle swarm optimization algorithm or something like that. And so this would be an algorithm that we don't cover in class, but I am going to do this project to explore how this algorithm works, what its strengths and weaknesses are relative to other algorithms, and demonstrate its use in a test problem that I designed. And that test problem could be a relatively conventional test problem, but a lot of people have fun with it. And they say, well, I'd like to build I did this RL thing with trying to build an agent that plays an online game in the best way, and and that where I really enjoyed that. So I'm going to actually then apply this to that instead. So it doesn't necessarily have to optimize a mathematical function or something like that. It could be I have a simulation of a robot that has a bunch of parameters in it, and I would like to optimize those parameters so that this kind of computer designed robot is able to walk across the floor in the fastest way or something like that. So you can pull in things you're doing in your own research. So if you have those tools, you just like to apply this, or you can do something a little more conventional, and you can say, well, how's what is a more general test function that I want to apply this to? So there's a lot of freedom in what to do here, but the idea here is that you get to explore an algorithm that we didn't explore in the class. You do it with a partner. So you'll submit your partner, you'll submit your choice of algorithm. That will be a short one, and I just basically check off on that. You submit a proposal, which basically is going to say, and this will be a short, like a one pager, that'll say, this is how we've already chosen this algorithm, and this is roughly the sketch of what we're going to do to demonstrate how this algorithm works. And so you put that in here so I can check off on that to say, that sounds feasible, or that sounds too complicated. Maybe simplify it. And then I leave you alone for a while. And then in the last week of the semester, in the middle of the week, so this will be due on Wednesday of the last week of classes. Then you submit a video presentation online, so not in class, and a report online. So this is an extended abstract. So it is relatively short. It's like a 4-pager. And there'll be information about that online. And so you submit this as a group to Canvas. And the reason I do it on Wednesday is because then I do a peer evaluation. And this will be due on the I think the Saturday right after the last week of class, in between the last week of class and finals week. And so this I'm actually thinking about trying this in Perusal. I used to use the Canvas-based peer evaluation system, which I don't particularly like, and it limits what I can do with peer evaluations, but peer evaluations have been added into Perusal, so I'm going to probably try that, and that might change exactly how this is structured. But it's still going to contribute to the same amount. I'll just may have to spread it out in a different way to make it work with the Perusal configuration. But the idea here is that you submit your report on Wednesday, and then you get assigned randomly the report and a presentation of another group, and you evaluate their report and configure and then submit your evaluation. You get points for submitting the evaluation. You then also get points for your own report and presentation being scored. And that's how we do it. So then the only thing that will be left again will be then that take-home final exam. So again, this is take-home, or I could say Canvas-based. This is non-proctored. Yeah. All right. And so that's basically how the assignments are laid out for this course. Okay, any questions about those deliverables? Okay. So again, just highlighting all of the drop policy here. The graduate level course, it's not meant to be burdensome in quantity of work. It's meant to be burdensome in quality of work. So hopefully the things that you choose to do are enriching and things you can spend time on and get a good return on, as opposed to a bunch of things you don't get a return on that you just have to do a lot of. So that's the sort of the goal in this design. Okay. All right. And so I just sort of mentioned here. So some of these, the dates in general. So I mentioned there's dates all throughout here. Some of these dates may need to be adjusted. There's some weirdness about uh, the way I don't know, there's something that fell weird in this week, so that like it didn't quite cause things to be aligned from when I imported things from the last time I taught this in the spring. So there may be some massaging of some of the dates that are currently on the Canvas calendar, but they will be massaging of things that where you've got plenty of time to deal with, and they won't move that much. But I just need to go through and make sure I'm really comfortable with them being there, and so on. Yeah, and then yeah, the grade, scoring, that's basically the plan there for scoring. Otherwise, late policies. So there's a bunch of these due dates I keep mentioning. I have built in an automatic grace period. So if something in almost every case, except for very special cases that are spelled out, almost anything that is due at a particular time, like if it's due at 11:59 Sunday, I will just make it available on Canvas through 10 a.m. the next morning. So if you don't get it in to the 11:59, Canvas may tentatively give you a 0 just because it does it automatically when it passes that due date. But as long as you submit while the assignment is still open, and it will be open till 10 a.m. the next morning, then it'll be scored. And when it gets scored, it'll replace that 0. So there's no penalty. There's no late penalties or whatever. As long as you get it in before the availability window closes, you're fine. After the availability window, though, it's done. So there's no late policy period or anything like that after that. Just make sure you get it in. So that's just meant to be a kind of no fault grace period that's built into there. There are some special cases. So I think I mentioned like here, like the final project stuff. Um, this might work a little bit differently as I move to Perusal, but at least due to the mechanics of how peer review works in Canvas, I can't close an assignment and leave the peer review open. So when I say to you, it's due at 11:59 Wednesday night, the last week of classes, it really needs to be in at that 11:59 because I need to assign the peer reviews, and so people will have enough time. And so even though the assignment will be available, it that availability is just there for the peer reviews to be available. And so if in those special cases, and I'll emphasize that as we get to them, then you really have to get them in by that due date, even though there is extra availability. So, but there's very few things that are like that. I think it's just going to be only the final project. Almost everything else has got this automatic 10 a.m. grace period the next morning. Grade correction policy. So once your grade is returned to you on Canvas, you've got a week, and then after that week, then I don't entertain grade change requests, and that's just so I don't want to set up the case where the last week of class where I'm trying to focus on your final projects and I just get a flood of grade change requests. And so just make sure if you get it back, you don't have to look at it immediately, but look at it within a week. Make sure you're okay with the grade. If you're not okay with the grade, totally fine. Just send us a note. But so the week there is the key thing. If you do send me a note over email, and again, other things are fine, Slack or whatever, but if you send over email, this isn't the only class I teach this semester. And so and there's a bunch of other emails I get on other things, research and grants and all of that. So in order to flag your message and bring it to the top of my attention, and it also helps me see, like a lot of times somebody will say, hey, Ted, I'm in your class. And then I'm like, I don't know which class, and actually Canvas doesn't allow me to like do a reverse lookup where I'm like, here's a student, where do they fit? So it really helps if you put in your subject either one of these terms, IE 598 or CSE 598. And 598 is not enough because the other class I'm teaching is Bio 598. But as long as you have those things together, it'll get flagged properly. It'll get put to the top of my inbox and I'll see your message. But if you don't do that, then it can get buried in a bunch of other things and it makes it harder for me. So make sure to put those in there. Or, if you send over Slack or Canvas, those could automatically get binned in the right spot anyway. So that's another option. Other things to highlight, this is sort of standard policies here and on academic integrity. I'll mention Title IX. So, this is again pretty standard and you've seen it in all your courses. But there's a class, there will be group work in this class. If you notice anything that related to harassment or sexual discrimination, then of course we want to know about it. Do know that if you report it to me as an instructor, I'm a so-called mandated reporter, which means I have to report it up the chain. So if that's not comfortable for you, then as mentioned here, there are counseling services who are not mandated reporters that you are welcome to, alternatively seek out. And so that's, just I need to say that so that in case hopefully nothing will happen, but if anything were to happen, you just know who to talk to and what are the consequences of who to talk to. All right. Students with disabilities, if you're registered with sales, I'm very happy to work with you. So just go through that registration. It's no problem. We can do extensions and, add a time and whatever you particularly need, but just make sure to register with sales. And once that's in there, then no trouble. Otherwise, recording devices and course material. So, I give you a lot of course material. That course material you can view as copyrighted material. Please use it on your own to help you with the course, but don't sell or distribute notes. Even your own notes, although that's technically copyrighted to you, it's against ASU's academic and integrity policy for you to sell your own notes without permission of the instructor. So at least while you're at ASU, then keep your notes to yourself. Of course, you can work with other students and things like that, but just sort of emphasizing, please don't upload things, because we're saying formally in this course that we don't have any prior permission to do that. Otherwise, I think that is the end of the syllabus. So those are all of the policies I wanted to highlight before we talk a little bit about the motivations for the technical content of the course. So are there any questions about course policy stuff? Okay. All right. Okay, so not a lot then to talk about today, but I do want to define a few key terms, and so kind of set us on our path to set something for a context so that on Thursday we can hit the ground running, sort of knowing why we're talking about certain things and where we're going. So, yeah, this course, bio-inspired AI and optimization. And so, the optimization part, there you go, lots of curvy functions. And then the bio-inspired stuff, well, there are, lots of bio-y type things. So we're going to be talking about bacteria, we're talking about DNA, we're talking about ants, we're talking about bees. We'll be talking about the immune system, talking about a wide variety of things and how these things map to engineering problems that are interesting and complex, and what we can learn from the natural systems here about how to solve the kind of unnatural systems here. And so, some terms that are going to come up in these first few units are heuristics, metaheuristics, and hyperheuristics, and how those relate to these things here. So, in their first couple units, are going to be in the context of optimization. All right, so what do I mean by that? All right, so let's imagine, and let me pull out my own set of notes here to make sure I don't lead us astray. So, and I'll write to slow myself down. Okay, so let's consider an example of driving a vehicle. So, and again, these are notes that, this PDF will be available after class. We'll upload it to Canvas here, but so we're driving a vehicle. So, vehicle falling behind another. So you've got the ego vehicle here. Let's say it's a human driver. Let's say you're driving in it, and it's following behind another vehicle here. And there's this question of distance. So distance. And the question is, what is the right following distance? And you can make lots and lots of choices here. So this, its ego vehicle could get very, very close to the following vehicle. It could stay very, very far away. But there's going to be pros and cons of each one of those things. And so you can imagine that, how to choose distance. And you could say, well, um, what are the um, what are the downsides of following very, very close to that vehicle? What could go wrong if you follow very close? What was that? You can collide, right? There's a risk of collision. So, too close, um, you've got collision risk. So, okay, great. Well, then in that case, I'll just back up way far away. But what's the downside of being very, very far from that vehicle? Um, by increase, we say, what do you mean increase traffic? Oh, well, so yeah, so it's going to have a societal burden for sure. So, if I'm too far, there might be a burden on others if it's a one-way street. But then also, like, is it good for me to be really, really far away from it? You can lose the. I mean, you can, yeah, if you were trying to follow. I'm just saying. Let's say I'm not trying to follow this vehicle; they just happen to be in front of me. So what are the downsides of I just want to get from point A to point B, and there happens to be another vehicle that's in front of me that I can't go around. So what's the downsides of maintaining a lot of distance? Yeah, that's right. It'll take me longer. So if I'm too far, it just takes me longer to get to destination. So there's trade-offs here. And we're always navigating these trade-offs. And so, when we drive, then, you can try to think about like this particular problem. I could think about this kind of mathematically. So, let's bring, it's weird that it didn't, but it gave me a white template. Hold on a second. Let me, or maybe I'll be stuck with a white template. Hmm. Well, that's weird. Well, as long as I can write, I guess it's okay. So, I could model this kind of, there we go. Um, if if I think about these things, kind of quantify them, then I could put following distance on this axis, and I can think there's some utility to me. And so maybe I'll call following distance X, and then I've got some utility to me. I'll put in quotes, f of X. And so without kind of figuring out how to weight these things against each other, I generally know there's a rough shape of this thing that looks kind of like this. So here is, this is too far out here, and this is too close. So if I have a way to aggregate these two considerations, the risk to me of getting in collisions, but also the benefit to me of of actually reaching my destination before the thing that I'm trying to get there, whatever the cost is of getting to my destination late, I can bring those two things together. And clearly, it's not so great to be close and it's not so great to be far, but there are some intermediate distances where it's not so bad. And there is some perfect distance right here. So this here maximizes my utility. And so I'll just call that distance X star. And we'll call this my optimizer. This strategy, this following strategy, balances everything perfectly. This is the distance that I should follow. But the problem is, it's really hard to know what that optimizer is. If you're driving a vehicle, there's, like, there's no, you, when you look around you, there's all sorts of things you could be observing, and you're taking those things in and you're trying to decide what following distance you want, on that particular vehicle. And you somehow have to make a decision. And you could claim that you make the optimal decision, but there, probably you haven't gone through and done all of the math. You probably don't have a way that guarantees that you're following at exactly the right distance, which perfectly balances these two concerns from being too far and too close. So in reality, you use another rule, like you might, for example, use the so-called 3-second rule. So does anybody know what the 3-second rule is when you're driving? So do you want to describe it? Okay, so you stay 3 seconds behind the car in front of you. And that says that this nice feature that at low speeds, then you're close, and at high speeds, you are far. It naturally stretches things out. It's a clever little strategy that automatically sort of, without, doesn't matter, you don't have to calculate, your speed and so through some formula. You don't have to sort of figure out, am I in kilometers per hour or miles per hour? It's just this nice simple formula that if you look at a point on the road that a car in front of you passed, you adjust your speed so that you don't hit that same point until 3 seconds later. And that will naturally shrink the space or spread the space out. So it's a very simple rule. It probably is not optimal, but it tends to get you where you want to go, and it helps you sort of balance the risk so that you're not way too far back, but you feel like you tend to have, you probably, so I'll say probably have stopping distance or stopping ability. So you don't know for sure what the stopping distance of your vehicle is. It depends on your brakes, depends on road conditions or whatever. But under most road conditions, this will tend to make it so that if the car in front of you slams on its brakes, it's going to eat up a stopping distance. And if you slam on your brakes within a reaction period later, you're going to eat up a stopping distance. And at no time, as the two vehicles are stopping, you'll collide into that vehicle. But meanwhile, you're close enough to that vehicle that you feel like you're actually getting to where you're supposed to be going. So that is a clever little rule that tends to work. Very likely is not optimal, but is probably good enough. So I would say that that probably fits. It's not up here, but it's probably somewhere, let's say, up here. It's in this realm of possibilities. So, these options here. So we could map those down, and we have this range here of what we're going to call, these here are good enough. And these strategies that are good enough, but probably are not optimal, we refer to as heuristics. So it's just a rule that it takes in, is based on some, time. I'm just going to say I'm going to use the time between me and the other vehicle, and I'm going to use that to set up a mapping to distance, and that time to distance mapping, that's how I'm solving this problem, and it's going to put me in this range somewhere in here. And that's a heuristic. It's a good enough solution. All right. Are there questions about that definition? What I mean by a heuristic? So you have your optimizer, and then you've got your heuristics. And and your heuristics are close to the optimizer, hopefully, if they work well, but there's no guarantee. All right, so this isn't the only heuristic that you could have chosen. So there could be, this might be this heuristic here. Like, let's say this is the 3-second stopping rule. It puts you right there at that particular distance. And that's, pretty good, but it's certainly not optimal. But there are other heuristics like here and here. So these are other heuristics. I mean, one of those other heuristics is the 2-second rule. Maybe 3 seconds is too conservative for you, and so you do a 2-second rule instead, or a 2.5-second rule. We don't know what's best about that. So there is a parameter of the heuristic that we can adjust to make for better or different heuristics. So I guess I should introduce that term as well, or this idea of parameters. And so we're going to say here that there are degrees of freedom in a heuristic. I don't know why there's this like delay in loading this graph, but I'll just guess it write it here. So well, all right, I'll just wait. And whatever is going on in this, I'll sort of experiment with this. It's been a while since I've used GoodNotes projected this way, and it's never acted like this before. So I don't know if there's been an update or something. But I'll just give it a second. So, and I'll write this down once it comes up, but the parameters of heuristics, well, we're going to call that parameters. Parameters are degrees of freedom of heuristics. So you can build heuristics based on lots of things, based on the time in front of you, based on the road conditions, based on how tired a person is. There's all of these different things that could go into the rule that sets your following distance. Each one of those things we're going to refer to as a parameter. So it's not a dynamic thing that is changing with the problem, but is a configuration option you can choose that today I'm going to use the 3-second rule, tomorrow I'm going to use the 2.5-second rule. And I'll just maybe go back into Zoom and then hop back into GoodNotes and see if that'll wake it up. Or maybe I just need to swipe away GoodNotes and come back in. Sorry about this. All right, let's try this. Always these day one technical things. There we go. All right, so degrees of freedom. So we're going to say that heuristics have degrees of freedom, degrees of design freedom. And we're going to refer to these as parameters. And so, that was an example of like, what time delay to use. Attention, road conditions, color of car. These are all different things you could use to build different heuristics for this problem. And your choice to use some and not the others are your choice of different parameter settings. And so we're going to refer to these as parameter settings. A neural network is a heuristic. It has a wide range of parameters. It basically is mapping inputs to outputs. The inputs come in, you train the neural network, we'll get to that here in a second, and then it produces an inference. It says, I think that this is a safe distance. I think this is a unsafe distance. So that's a classification neural network. And so, those weights of the neural network, those are parameters, which can be chosen in a wide variety of ways. And there's probably a bunch of different neural networks that perform very similar to each other, just like there's a bunch of different driving heuristics for this particular following distance that work very similar to each other. Some of them might are less complicated to implement than others. So, there might be, if you're implementing a neural network on a drone, on a little quadcopter that has a Raspberry Pi that's sitting on top of it, you might have to build a very, very small neural network, but it's solving the same problem as if you had some sort of NVIDIA Orin Jetson Nano on top of your drone that can fit a much larger neural network on it with many, many more parameters. But they might be taking roughly the same inputs and giving them roughly the same outputs. And they probably neither of them are doing the optimal thing. They're just doing something close to the optimal. And so these are all different ways you could set up these parameters. And so, the question is, how do you train a neural network? How do you choose these heuristic parameters? And that is what so enters the metaheuristics. So these themselves are heuristics for choosing parameters of other heuristics. So what do I mean by that? So you can think just as just as a car is moving through physical space, a meta-heuristic can move through the space of all possible parameters. And so a meta-heuristic can guide the design of a heuristic. So a meta-heuristic like we'd use in this class might, for example, you'd say, hey, meta-heuristic, hey, genetic algorithm, I don't know the best way the best time distance to drive in normal road conditions. So I'm going to build a simulator of a car that needs to get from point A to point B. And I'm going to subject it to other cars with behavioral models of real human drivers on them. And it has to choose how to follow them. And I have the ability to run thousands of replications of this car going from point A to point B and count up how many times it gets into a collision and how fast it gets to its destination. And I can try those with a 1 second rule, with a 2 second rule, with a 3 second rule, and so on. But there's so many different choices I can make that I can't try them all. So what I'm going to do is ask you to search through this space in a smart way and have you tell me what the best heuristic is based on your search through there. And that meta heuristic will itself use a heuristic to figure out, well, I got a pretty good result with 3 seconds. So I'm going to just perturb that a little bit off and try 2.5 seconds and 3.5 seconds. And based if 3.5 seconds is better and 2.5 seconds is worse, then I'm then going to try 4 seconds next. So it will have a rule for how to move from one parameter to the next based on its experience in the past. This is very much like reinforcement learning. Reinforcement learning falls into the realm of metaheuristics. But in this class, we're going to be learning about other types of metaheuristics that are inspired by other approaches that do it in a very different way, but solve a lot of the same problems. So that is this metaheuristic, is it sort of is itself a usually a sort of an approach or rule for moving through a large space of parameters that configure lower level heuristics. And an example here, stochastic gradient descent for neural networks. So back propagation. If this is not something you're feel really familiar with, that's fine. For typically there are students who have some background in this, is why I bring this up as an example, but it's not a critical example. But the point here is that artificial neural networks have got a bunch of weights in them, and there are a bunch of approaches that attempt to optimize these weights, and they are motivated by formal optimization problems. But an ANN is not x squared plus 5. It is not a simple function that if you happen to find the spot where the derivative equals 0, then you've reached the optimizer. You're probably never going to get to a point where you find the weights that make your loss function's derivative equal to 0 exactly. But you're going to use the loss function for the ANN to guide your next choice of the weights to choose. And that's what things like stochastic gradient descent do. They sound formal. They sound like there's guarantees here, but there are no guarantees. These are just metaheuristics. They are heuristics for searching through the space of parameters of an ANN, and you have no guarantees that they'll actually produce a good solution. But they tend to produce a good solution. Probably not the best solution, but they tend to produce a good solution. So that's what we mean by metaheuristics, is how to search through these parameters. Now, if anyone here, how many people in the room have done a neural network problem where you've had to train a neural network to solve? Okay, so that's fine. So you probably had to at some point choose an optimizer for your neural network, Atom or something like that. And that optimizer itself probably had parameters. You may have left them at their defaults, or you may have played around with adjusting those parameters. Heuristics have parameters. Meta heuristics also have parameters. And so then the question is, what are the best parameters for a meta heuristic? Well, then enter, wait for it, literally. So I think this worked last time where I closed this guy, came back in. I'll have to do some practice with this at home to see what horrible thing has happened to GoodNotes and how we can fix it. Generally, I find GoodNotes to be an excellent note-taking tool for the iPad. If you've not used it, I know a lot of students do. Um, Highly recommend it, except for today. Metaheuristics have parameters. So then the question is, how do you choose metaheuristic parameters? Well, then enters finally the hyperheuristic. And these are heuristics that search the parameter space of metaheuristics. Oh, like the erase isn't working. There we go, metaheuristics. And by the way, the parameters of metaheuristics we refer to as hyperparameters. So you get this sort of turtles all the way down type of feeling here, where you've got heuristics helping you with heuristics, helping you with heuristics. Hopefully, what's happening though is that once you get to the realm of a hyperheuristic, hopefully this will have far fewer parameters itself. So the idea here is that you've got a really complicated heuristic, a artificial neural network. It's got a million parameters, a million weights. So then you use a genetic algorithm or stochastic gradient descent or whatever to optimize it or to attempt to optimize it because you're never actually going to optimize it. And that itself has got 15 parameters. Well, that's a lot better. That's a lot fewer parameters, but it's still hard to pick those 15. That's still a hard problem. So then you can say, well, rather than me trying to tune all these knobs, I am going to do one last heuristic, the hyperheuristic, and give it access to those 15 knobs. It's going to run experiments with my metaheuristic, which run experiments with my heuristic. And it will hopefully choose the best parameters for my metaheuristic that will choose the best parameters for my heuristic. And then hopefully that hyperheuristic itself will only have one or two parameters, one or two knobs that I give an opportunity to tune. So overall, it should make the optimization process easier for me, but it probably will maybe make the process and I have to be careful about this, maybe take longer because now you're unleashing an automation system to tune another automation system to tune a heuristic. And it may be that your hyperheuristic is has to do a lot of exploration to figure out how to optimize your metaheuristic to figure out how to finally optimize your heuristic. So it has the potential to do a lot of tests in order to make this work, but it maybe makes it easier for you. Now, if you happen to know that your hyperheuristic you can constrain your metaheuristics parameters. If you can constrain the hyperparameters, then your hyperheuristic, maybe you can tame it a little bit, and so that you can reduce this. But still, there is kind of a speed accuracy trade-off here. So yet another type of trade-off where the if you just live with the default parameters of your metaheuristic, then you can get the job done quicker. But the hyperheuristic hopefully makes the ultimate solution better, but it just maybe takes even longer because now the hyperheuristic has got to run your metaheuristic over and over and over again. So if you don't have that many computational cycles, maybe you just live with the defaults that come out of your metaheuristic. But that's kind of the general idea of why we have these different layers here. But I just want to emphasize these all are heuristics. And the one other place where we see lots of heuristics is nature. So nature is full of heuristics. And so generally we don't think that things that are walking around and crawling around and are going through, that are they're floating around in our blood, we don't think that these are optimal in any particular way. But we do think that they're shaped by pressures that are optimization-ish. So we think that, if you can fly faster, you're probably going to do better as a bird. And so, birds that fly faster may have to, be able to do better if they're, say, predators. But maybe if you're a small bird, flying faster isn't that useful to you because you never can fly as fast as the big birds. But maybe you can be more maneuverable. So there are certain selective pressures where at certain configuration sizes, it's better to be more of one thing than another. And at other configurations, it's better to be another thing than another. And this creates pressure for things to move in directions which tend to be kind of, lots of good enough and better than. And so this is sort of this is basically kind of a hinting at natural selection. It is a tool for competition, but it is not a perfect optimizer. So when we look, for example, there's a really nice paper written by a couple of MIT researchers about drones that fly through forests. And when people that were building drones wanted to have 100% safety when they're flying through very cluttered forests, then the 100% safety condition would mean that the drones had to fly so slowly that they would almost always die in the middle of the forest in terms of battery life. And so these researchers noticed that birds fly very, very fast through forests, and you know, they rarely hit trees. And so what they found is they did a bunch of these simulations, and they saw that in these sims, and I'm about done here, but in these sims, that under a critical density, it didn't really matter how you flew. There was, as long as you did relatively simple maneuvers, then you was almost 100% of the time you would make your way through the forest with no collisions. But over a critical density, then it didn't matter how you flew, unless you were going super, 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 super slow, you would always hit something. And so as long as you were under a critical density, it was sort of dumb to optimize your planning algorithm to try to slow down and move around these things, because a relatively dumb flight planner would be able to get through these trees and almost never hit them. And so he thought that's probably what's going on with these birds. If you're a big bird that moves so fast, if there's a forest that's above that critical threshold, you're just not going to live there because all the birds that tried to live there before died. But in anything that's under that threshold, then you can fly through that thing and you don't have to worry about it. You don't have to have the optimal trajectories. So that's an example of, that's a heuristic that works. And so they were then arguing that people should be taking this kind of percolation idea, this idea that there's different types of cluttered environments, and just figure out which one you're in and stop optimizing and just build a relatively simple planner that is, tailored, that is not tailored, but that is under that critical threshold, because then it'll work for a wide range of things. You don't have to worry about it being specified to that. So that's an example of a heuristic there. So that, the flight heuristic is one thing, but then how you even get there, that's kind of evolution, natural selection. That in itself is a heuristic that is selecting certain animals to survive in certain areas and other animals to survive in other areas. So that in itself is a heuristic, and so on and so forth. And so what we do in this class is try to understand the computational principles and the dynamics underlying some of these natural systems, and then see what inspires us for how to build better metaheuristics, for example, in order that helps us craft these heuristics, these solutions to these hard problems. When you don't have something like, I mean, the artificial neural network, differentiable loss functions have been super important because they've been able to leverage calculus as their source of inspiration. But not all loss functions are differentiable. And the types of metaheuristics that we talk about in this class are in that scope where you can't just resort to calculus in order to solve things. That's kind of where we're going to start then on Thursday. That's our motivation. That's all I've got for you today. Thanks for your patience and look forward to continuing that. So have a good day.